Hello, I'm Patrick Gilreath, and welcome to my real-world application video. In this video, I have asked my father to explain how he uses trigonometry in his work. He works as a piano specialist, and this example that I'll be showing you has to do with building and repairing a piano. Some of the pianos he's worked on can be over a century old and can cost $100,000, so you can see why trigonometry would be important so he doesn't mess up and ruin the customer's day.
Good afternoon, I'm Alan Gilreath, and I would like to talk to you a little bit about how we use trigonometry in rebuilding pianos today. In rebuilding pianos, we have to deal with some very precise, very exact angles, and we have to determine how to calculate those angles. I'm going to use a few terms that are a little bit unfamiliar to you, but I hope that I'll be able to explain those as we go along. In a piano, there's a large sheet of wood called the soundboard. The soundboard is what transduces the mechanical vibrations into sound that we can hear in the air. That vibration comes from what we call a piano string, which is actually a piece of steel wire that is stretched from one point to another. In between those points is a device we call a bridge. The piano wire has to contact the bridge. This is a sample of a bridge, which is then glued to the soundboard itself. Now, that is a very shallow angle that this string approaches the bridge, goes across, and leaves on the other side. So what we have to do is determine how thick to make this bridge within thousandths of inches to make sure that we have the right amount of pressure bearing down on the soundboard. You'll notice, if you look very closely, you can see the main body of the bridge with vertical stripes. Those are pieces of wood that are glued together. On the top is what we call the bridge cap, which is a solid piece of maple. The body of the bridge is a given height. The cap is what we adjust when we're building a piano or rebuilding a piano to determine exactly how much pressure we have pressing down on the soundboard. To determine how thick to make the bridge cap, we use a little bit of trigonometry. In many cases, we use a 1.5 degree angle for a net bearing across the bridge. This demonstrates the soundboard is the bottom line. This line, if you look closely, is the plate where the string attaches. That is a cast iron plate that is very thick. So let's make that a little bit thicker so you can see how thick that is. That's thick like that. The string comes across and attaches to the hitch pin, and then we have a bearing point. And this is where we're going to measure to, is this bearing point. Here we have the bridge with the bridge pin sticking up, the string leaving at a downward angle, leaving the front portion at a downward angle, and then the front of the string is pressed down by this device. We won't even go into what that is. Now, in order to determine the thickness of a bridge cap, we will start out with the bridge root, the vertical laminations we looked at earlier. We will stretch a string from the bearing point at the front above the bridge, and we will set it at a height above the bearing point, which is on the plate back here. Now, to determine how high to set this angle, we have to do a little bit of calculation. Once we have this height determined and measured, we can measure the distance between our bridge root and our resultant point of the string to determine how thick to make our bridge cap. Now, if we want a 1.5 degree angle, we use the sine of 1.5, which happens to round off to 0.0262. If the distance from where we touch the bridge to the distance above our back portion is 1 inch, then we measure that distance as 0.0262. If it's 2 inches, we can calculate it on each distance as we go along, but when I'm working, I keep a table of the sine of various angles multiplied times various distances, and I work in tenths of inches for ease of calculation. So all I have to do, on this table I have the 1.5 degree, the sine of 1.5 degrees highlighted. If I have a 5.3 inch distance from here to here, I will multiply the sine of 1.5 times 5.3 inches, and that gives me a height here of 0.138 inches. If I put a thickness device 0.138 inches here, then this string will be suspended above the bridge. All I have to do is measure this distance, which will be smaller than 0.138, obviously, and that will let me determine exactly, well, sorry, it will be more than 1.138 because this is lower. But it will let me know exactly how thick to make my bridge cap so that I have a contact point right there, giving me a net result of 1.5 degrees on each node of the scale. So we can change that very easily. It's easy to calculate by using the distance. We can use the sine of a different angle if we want to do 1/2 degree, 1.5, 2 degrees, whatever we happen to need for the piano. So this is a very simple application of trigonometry in piano rebuilding. There are a lot of other factors that go into it, but this gives you the basic concept of one place we can use it very easily. Thank you for your time.
And then, whenever you get all of those things and add them together, this is the result. Well, hey, it's me again. I just wanted to thank you for watching my video, and I am glad that you hopefully enjoyed it, because, well, you lasted this long to get to the ending, so... But anyway, I hope that this satisfies the requirements for the trigonometry real-world task, and I just hope you have a nice day. Bye.